Suppose you're given the following velocity versus time graph, and you're asked to calculate the total distance that this object travels in 10 seconds. Now there's two distinct regions of this graph. There's the 0 to 5 second interval of time during which the velocity is going to increase, which means that during that first 5 seconds of time, that object is going to be accelerating, in this case, at a constant rate. Then there's going to be a second 5-second interval of time between 5 seconds and 10 seconds, during which this object is going to travel with constant velocity. Now, before we begin, let's just identify a few key points. There's this point here, and we can call this our initial velocity. Our initial velocity in this case is going to be 0 meters per second, and that corresponds to the point on the graph where time is 0 and the velocity is also 0 meters per second. And then there's this point after which 5 seconds this object hits a velocity now of 5 meters per second. And if I was to label that point, it would be the point 5 seconds, 5 meters per second. And what that's indicating is you start off from rest and you increase your velocity over a 5-second interval of time until you hit 5 meters per second. Then there's going to be the second region of time, between 5 seconds and 10 seconds, during which this object is going to be traveling with constant velocity. Now this point right here could be labeled as 10 seconds, 5 meters per second. So a few things. Notice that during this interval of time, the acceleration is going to be 0 meters per second squared. During this first 5-second interval of time, the acceleration is going to be something, and let's just calculate what that acceleration is right off to the side. Now your acceleration is going to be defined to be the change in velocity per change in time. And we can calculate this acceleration for an object traveling with constant acceleration. So in this case, it's going to be the final velocity minus the initial velocity divided by the time it takes to change that velocity. Now in this case, it's going to be 5 meters per second minus 0 meters per second. So 5 meters per second is our final velocity minus 0 meters per second divided by the time it takes to change that velocity, which in this case is 5 seconds. Now when you do that out, what you should see is that you get 5 meters per second minus 0 is 5 meters per second divided by 5 seconds. So 5 divided by 5 is going to be 1 meter per second squared. So this object increases its velocity by 1 meter per second per second. So now we can go back over to our graph and we can label that point as 1 meter per second squared. And now our first approach to determine the distance that this object travels during this 10-second interval of time is to use the geometric approach, which says that the distance this object travels equals the area underneath this velocity versus time curve. Now if you observe, there's two distinct regions. There's this first region, which is the area of a triangle, and then there's the second region, which is the area of a square or a rectangle. So the total distance this object travels, let's call it delta x, is going to be the area underneath the curve. Now in this case, this is going to be the area of a triangle plus the area of a rectangle. Now the area of a triangle can be written as 1/2 the height of the triangle times the length plus the height of the rectangle times the length of the rectangle. Now in this case, the height of our triangle is going to be this point right here, which corresponds to 5 meters per second. And the length of this triangle is going to be 5 seconds. So we can, in place of these two dimensions, we can write 1/2 the height, which in this case is 5 meters per second, times the length of 5 seconds, plus the region during which this object is traveling with constant velocity, which is going to be the height of the rectangle, which in this case is also going to be 5 meters per second, and the length of this rectangle is going to be 5 seconds as well. So the height will be 5 meters per second times a length of 5 seconds. Now in this case, notice that your units of seconds cancels out in both cases. So what you end up getting is 1/2 of 5 times 5, which is 12.5 meters, plus 5 meters times 5, which is 25 meters, or a total distance of 37.5 meters. So this is our geometric approach to calculating the distance. Our next approach will use the kinematic equations to determine the distance. Now to calculate the distance, recall that our kinematic equation, let's call this for region 1, the first 5 seconds of time, will be our initial velocity times time plus 1/2 the acceleration times time squared. Now in this first case, our initial velocity is 0, so the distance this object travels during that first 5 seconds of time is going to be 1/2 the acceleration of this object times the square of the time. Now in this first case, we said that our acceleration is 1 meter per second, so I can now write in 1/2 of the acceleration, which is 1 meter per second squared, times the time over which this object is accelerating, which in this case is 5 seconds, square the entire term, and what you should get is 1/2 of 1 meter per second squared times 5 seconds squared should be 25 squared seconds. And what you should notice is that the units of squared seconds cancels out and you get a unit of length. And when you do that, you should get 12.5 meters. And during the second interval of time during which this object is traveling with constant velocity, let's write this as delta x2, this is going to be the initial velocity of the object times time plus 1/2 the acceleration times time squared. Now during the second interval of time, this term here, this acceleration is 0 because the object is traveling with constant velocity. The velocity is not changing. So that term will be 0. And what you should see is that using the kinematic equation, the distance this object travels is just going to be equal to the initial velocity times time. Now in the second case, the initial velocity is going to be 5 meters per second times a time interval of 5 seconds. And what you should again notice is that this unit of second cancels out with this unit of second. And when you do that, you get 25 meters. And so the total distance that this object travels is going to be the sum of these two individual terms. So in this case, it will be 12.5 meters plus 25 meters. And this works out to be 37.5 meters, which is exactly what we got in the first case where we used the area underneath the velocity versus time curve.